So this video is about the electric flux. And flux, if you haven't come across that word before, it basically means flow of something through an area. In this case, it's the flow of the electric field through an area. And you might ask, well, what area? Well, you get to choose that. You get to find what area you're going to see how much electric field flows through. So let's go ahead and do an example. Say we have a uniform electric field. So it's always the same strength, it's always pointed in the same direction. Maybe it looks something like this. And then we're going to pick an area. I'm going to pick a flat one. And maybe I'll orient it so it's just like a piece of paper like this. There's my area. Now, the amount of flux, the amount of the electric field that's flowing through this area is going to be different depending on how the area is oriented. So like if I orient this piece of paper like this in the electric field, that would be a bit different than if I did it 90 degrees. So more like this. For the same electric field, one that's going like this, there isn't actually any electric field going through this area. It's just going across it, whereas here all the electric field lines are going straight through the paper. So apparently orientation matters. So mathematically, when we define the electric flux and we use this symbol here, this is a Greek phi, which is what we use for flux, and then to say it's the electric flux, we might put a little e down here in the subscript. We define that as the dot product between the electric field, which is a vector, and the area, which we're going to make a vector as well. So the magnitude of this vector is just going to be the area of the surface, so just what we normally would do if you were thinking of area. But the direction, that is going to be given by this little unit vector that is an n, and that is because it is called the normal unit vector. And I'm using normal here with a different meaning than I did before to mean like regular. Here, this normal means perpendicular. So if we want to know which way the area vector is facing, we will look over here at our area and we will pick a direction that is perpendicular to the surface. So this would be like the direction of the area vector based on the direction of this little normal unit vector. So perpendicular, 90 degrees from the surface of the area. Now, of course, there's a little bit of ambiguity here. We could draw the unit vector pointing this way, perpendicular, or we could draw it pointed out the other way. They're both perpendicular to the surface, and this is another thing where it's your choice. If you've got an open surface like this, you can pick either this side or that direction to be the direction of this normal to the surface unit vector. All right, well, now that we've got that defined, let's see how it works. This dot product, and if you don't remember how the dot product goes, well, you do it like this. You get the magnitude of each of the vectors that you are multiplying together, so the magnitude of the electric field times the magnitude of the area, or the regular surface area, times the cosine of the angle between them. And this angle, and that's a beta by the way, this angle here, the electric field pointing that way, the unit vector is also pointing the same way, so if you pick this one, the angle between them, that beta is going to be 0. Cosine of 0 is 1, so then the flux would just be the magnitude of the electric field times surface area. And if you happen to pick this other one, well, then the difference in direction between the electric field and the unit vector is 180 degrees. And cosine of 180 degrees is -1. So again, it's the magnitude, electric field magnitude times the area magnitude, but just with a negative sign in front of it. And that denotes that the electric field is flowing kind of backwards through the way that you're thinking of the surface pointing. So the surface area points this way, but the electric field flows the other way. So the flux picks up a negative. Now if we look at this surface, same field, but a different orientation for our surface, the normal vector here is going to point either straight up like that or straight down. One of those two. Just let's start with this one. Doesn't matter here, we have A is pointing up, E is pointing off perpendicularly. And the angle between those two is 90, or pi over 2. And cosine of 90 degrees is 0. So the flux is 0 through this surface, which again makes sense. None of the electric field's flowing into or through the surface, it's flowing straight across it, going across it like a sheet. So there's no flux in that case. So that's why we need the dot product as part of this multiplication to figure out how much electric field's going through the surface we picked. Now there's another kind of surface that you could do. I picked a nice flat one like this, but we could also pick maybe a curvy surface. Like this one, for example. And in that case, the direction of the area vector is going to depend on which bit of the area you're looking at. So right here, for this little bit of area, the area vector would look like that. And because it's just a tiny piece of the area, we'd need the little calculus infinitesimally small d alpha, or d area. If you're over here, different direction, different bit of the area. Over here, different direction, different bit of the area. So we need to modify the flux formula a little bit. This one works if you have a constant electric field and a nice flat area. More generally, you can write the electric flux like this. The electric flux is the integral of the electric field dotted with each tiny bit of area. So you have to integrate over the whole area. So this is actually a two-dimensional integral, because that's an area, so it's surface integral. But at each little bit of the area, you take the dot product with the electric field, and that'll give you how much electric field is flowing through this curvy surface. There's one other kind of surface you can get, and that is what we call a closed surface. A closed surface is any surface which is the surface area of a volume. So for example, let's do this cube. And I'll do kind of a block back here. As you can see, it's three-dimensional. Maybe a bit will make that little heart darker. But here we have a cube. And so then now our surface is the surface area of this cube. And of course, for the different faces of the cube, the area is going to have different directions. So over here, we might draw the area like that. That would be a little bit of area. Up here, its direction might point like that, still perpendicular to this part of the surface. Over here, might point like that. And you notice all of these area vectors I've done out of the center of the cube, and that's the convention. If you have a closed surface, that is one that encases an entire volume, then the direction of A is always out. It always points out of the volume that you're enclosing with this closed surface. And if we want to find the flux here, we have a mathematical way to denote that. We still have the flux, same signal. We're going to have to do an integral here because we have a surface which is changing. Still going to be two-dimensional because we're still looking at an area, which is a 2D sort of thing. Still have the electric field. So let's say it's still uniform. Maybe it's flowing like this. In this particular case, there's our area. Still have the dot product. We're still integrating over the whole surface area, but since it's a closed surface, we're going to change how we talk about the integral just a little bit. We're going to put a circle around here, and that says we're integrating over a closed surface, a surface which encloses a volume. And you know what's happened here. We have the electric field comes in one side of the cube and goes out another. And so because the area is defined as always pointing outside of the cube, that means when it comes in over here, it's going opposite this surface area direction. The flux will be negative, but then it's flowing out the other side where the area vector will point out, and it'll be positive there. So it kind of seems like it'll cancel. And the question is, are there any closed surfaces that have fluxes that don't do this cancellation thing, where you have a negative flux in and then a positive flux as the electric field lines flow out? Negative in here, positive it goes out the other side. And the answer to that question lies in Gauss's law.